So for example 5, we're trying to find a parametric representation for this cylinder. Okay, is x squared plus y squared equal 4, z between, bless you, 0 and 1. Okay, so I graph it over here. That's the cylinder. And z here, z equal 1 here, z equal 1 here, z equal 0 over here. So it's part of the cylinder between the two planes right here. Okay. All right. So now, how can I find a parametric representation? We had to actually decide which one to be, what parameter here would be the, which one is U, which one's V. Okay, we need to pick the parameter, right? So looking at this, it's a cylinder, right? So naturally, we think about the symmetrical coordinate, right? Okay, to represent this, okay? So do you guys, let's do a quick review about cylindrical coordinate over here, okay? Here I draw this, right? In cylindrical coordinate system, what does x equal to? Yes, very good, okay? The x over here is all sine beta, okay? And then what about y? Y is r sine theta, yeah, you got it. Okay, and then what about z? Oh, z is z. Okay. All right. Z is not z stay the same. That's in symmetrical coordinate system. Okay. So and then the data over here will go from 0 to 2 pi, okay, one rotation. And then for this one over here, the cylinder, z is between 0 and 1. Okay, so between these two. So think about the cylinder here, and you intersect with the two plane. It's this part here, that's between the two plane.
When you use the cylindrical coordinate system, x and y have to be expressed in terms of r and theta using this polar coordinate system. So what does x squared plus y squared equal to?
Did I remember? R squared. Yeah, you got it. Good job. Okay. So we have R squared is equal to x squared plus y squared in cylindrical coordinate, right? So over here, this one, x squared plus y squared is just R squared. So this cylinder has a simple representation, which is R equal to what? 2. Yeah, you got it. Okay. So, and then R equal to 2. Okay. And then the z has to be between 0 and 1. Okay. So now we can decide the parameter, the two parameter u and v, right? In this case, we're going to pick the r over here is fixed. Okay, r is 2. Okay, so we're going to pick this theta and z as the two parameter u and v. Okay, u and v right there. So this one, so the two parameter will be theta and z. And those are the 3 parametric equations right here. Okay. So theta and z. X is a function of theta and z, y is a function of theta z, and z is a function of theta and z. Okay. So x, y, z represent as function of theta and z. So those are the parametric equation. Okay. And then we also state the d. What's the region? What's the restriction on the data? Data is between 0 and 2 pi. What's the restriction on z? Z is between 0 and 1. Okay. Then this will be those parametric equation we're looking for. Okay. Okay, good job. Let's look at the next example 6. Could you find a vector function that represents this elliptic paraboloid right here? I graph it. Okay. I graph this elliptic paraboloid. Okay, this is a graph. Okay, like that. So we have to decide what are the two parameters. What are the u and v? Okay. What do you notice about the z? The z here is represented as function of x and y. Don't you notice that? right? So here you see that this z is a function of x and y. So actually, you want to pick the two parameter as x and y. Okay, so it's u and v, you're going to pick x and y as a parameter. Okay, so we're going to pick x and y as parameter. Then you can write the parametric equation. Okay, so what are the parametric equation then? So x will be equal to, okay, what should I put over here, you think? So this one here is a function x and y, right? So you can parameterize this using x and y, and use that. What about this x? X will be the x itself, right? Okay, and then y will be what? Y itself, yes. Okay, so next time you see that the z here is a function of x and y, then you can actually parameterize this surface just using x is x, y is y, and just put z equal to this. Okay, like that. Similarly, when say x is a function of y and z, and you can do similar thing, right, to get that. So that would be an easy parameterization. Okay, so if you recognize one of the coordinate as a function of the other coordinate, okay, then you can just keep that right here and using just let x equal to x here, y equal to y, and then this one equal to a function of the other two. Okay, like this. So what's the vector equation for this one? What should I put over here? After you get the parametric equations, then you can just put this in each component, right? So the x component will be this x, and then here the second component will be this y, and the last one here is this x squared plus 2y squared. So that will be a very easy way to parameterize this surface and to find this vector function. Okay. Question? Okay. Now here is the weak mark right here. So in general, a surface given as a graph of function of x and y, the one that we just have above, see this surface over here, it's given as a function of x and y. Then with the equation of this form, z equal to a function of x and y, we can always regard it as a parametric surface by taking x to be x, y to be y, and then the z here as this function of x and y. Okay, so we're using x and y as a parameter. So in this case, this one here will be the x, and this one here will be the y. So the u, remember you try to find out what the u, this two parameter is. So now you're going to let this x, this to be y. Okay. The two parameter, x and y. Okay. So x equal to x, y equal to y, and z will be a function of x and y. Okay. Okay. Okay, let's look at the next example, example 7. Okay. Could you find a parametric representation for this surface, which is the top half of this cone? This cone over here. Okay, this is the cone. Remember, had this top and then also had the bottom below. Okay. The parameterization is actually not unique. You have different way to parameterize it. Okay, let's think about an easy one. Okay, the first solution. From the common, the weak mark we just have, do you notice that here is z here as a function of x and y, isn't it? Right? So one possible representation is what? X equal to x, okay? Y equal to y and z equal to 2 square root of x squared plus y squared, right? So that's easy. And then the vector equation here, you just put them into each component, right? So x, y, and then 2 square root of x squared plus y squared. So the book here forgot the 2, okay? So you put the 2 back here, right? So that's one way, right? What about another way? Another one, we can actually use the cylindrical coordinate, okay? So because the cone here is kind of like a circular, like that, right? So think about the cylindrical coordinate, okay? So we're going to use Rn data as a parameter. So instead of letting this to be x, this to be y, we can actually pick the parameter here. Maybe we can let that to be R and this to be V. So when we pick the U and V, we can pick the Rn data as a 2 parameter. Well, it's still working. Good. Sometimes it might damage it. Okay. So we pick the 2 parameter Rn data this time. Okay. Now we just review the cylindrical coordinate, right? X is R cosine theta, Y is R sine theta, right? So now Z is 2 times square root of x squared plus y squared. In cylindrical coordinate, x squared plus y squared equal to what? Huh? Oh, that's equal to r squared, right? And square root of that is r. So then this one here is equal to r. Yeah, you got it. That's equal to 2r. Yeah. So let me write it down. So that is equal to 2r. You got it. Okay. All right. So a vector equation for the cone is what? So the first one here, this is for the x, right? And this is for the y, and this is for the z. Sorry. Okay. So now we can put the component in, right? X is what? What should I put here in terms of Rn data? Yeah, it's R cosine theta. Okay, good. And then Y will be what? R sine theta. And then Z will be what? 2R. Yeah, you got it. Good job. Okay, this one. So this is another way to parameterize it. Okay. Now, which one's better? This one better or this one better? Okay, but we also need to, this one here, we also need to put down the restriction, right? Data here. Okay, the data should be go from 0 to 2 pi, and then R here go from 0 to, oh, there's no restriction on the R. The R actually go to infinity. Okay, 0 to infinity. Okay, all right. Over here, for some purpose, the two parametric representation, they're equally good. Okay, so we have two. One is this one over here. Okay, and then we also have this one over here. Now they are equally good. Okay, two different representation. Okay, but the second one might be preferred in certain situation. Okay, if you're interested in only like part of the cone, okay, for example, like this cone over here. So if you want to say the cone below the plane z equal to 1, then this one over here might be easier, might be a better representation. Okay, so suppose you want this cone below the plane z equal to 1, and I'm using this representation, then what will be the domain for those parameters? R is between what and what? So say Z is equal to 1, this plane over here. R is between 0 and what? R is between 0 over here, right? and then all the way to what? All the way to, I think it should be 1. Okay, let me see. Oh, 1 R is, oh yeah, the Z is equal to, remember the Z over here is, so Z is equal to 1, right? Z is between 0 and 1. And then remember Z is 2R, right? Z is 2R. So 2R between 0 and 1. So R is between 0 and 1/2. So R is between 0 and 1/2. What about data? Data go from what to where? Looking at the cone. This cone over here, data go from 0 to 2 pi. Yeah, you got it. 0 to 2 pi. Okay. All right. Okay, next one, let's review the surface of revolution. Okay. Let's talk about this. Do you guys remember surface of revolution, right? Okay, let me refresh your memory first. This is the formula to calculate the surface area, okay, for the surface of revolution, right? So how did we do that before? So suppose we have this curve over here. When we revolve this about the x-axis, then the surface area is going to be the circumference of the circle of the point on this curve. So that will be 2 pi y over here. And then this part here will be the differential arc length, the dx, which is going to be 1 times dy dx squared here dx. And the x here goes from into p. So that was how we found the surface area for the surface of revolution in the past. Okay. Now go back to this. Okay. Now this one over here, this is actually the surface of revolution. Okay. And now let's think about you revolve this y equal to f of x here and now revolve that way. Let's think about the x coordinate here. Let's parameterize this surface. Okay. I'm gonna let x to be just x. Okay. Because over here it says y here is a function. Okay, so here. Okay, let's see. Y is a function of x. Okay, so naturally I'm going to pick one. Remember, we're trying to pick the u and the v, the 2 parameter. So one of the parameter I'm going to let that to be x. Okay, so 2 parameter. Okay, it's x. Okay, and then the other parameter I'm going to pick will be this angle. This angle here, theta. Okay, this angle that you rotate the theta. So you have 2 parameters. Those are the u and v. Okay. Okay, so if we do it that way, then x will be just equal to x itself. What about the y coordinate? Take a look at the y coordinate at this point. The y coordinate at this point over here, I'm going to highlight this. So that is going to be, isn't that from here to here? Okay, let me do it this way. Okay, is it from here to here, right? This is the y, okay? That's the y coordinate, okay? From here to here, how is this one? Okay, remember when you revolve, okay, this is y equal to f of x. So when you revolve, the radius of this circle should be f of x. So we know that here to here is f of x, and here is theta. How do you find out this y over here? That's the adjacent side of this y triangle. Adjacent side of this angle theta. What does this equal to? That will be f of x times what? Cosine of theta, right? This is adjacent side of this angle in this y triangle. So that will be this f of x times cosine of this theta. Okay, good. All right, now what about z? Z is this one, right? Z is this one. this is f of x. This is theta. Z is opposite with this angle. So what does z equal to? F of x times what? Sine of theta, right? Okay, sine of theta. So now we use the two parameter, okay? We're going to have x and theta as the two parameter. So x is x, y is f of x cosine theta, z is f of x sine theta. We're able to parameterize this surface over here, okay? The x over here go from what to what? Theta go from what to what? Well, looking at this diagram here, x go from A to B, right? Here, x go from A to B. So x go from A to B. What about theta? Theta go from what to what? 0 to 2 pi. Yes, you got it. 0 to 2 pi. Okay, so you finish one rotation. Okay, good. So you parameterize this surface of revolution this way, using x and theta. Okay. Next example. Find parametric equation for the surface generated by rotating this curve about the x-axis. Well, we actually use a computer to generate the picture. Rotate this about the x-axis, you get something like this. Okay, kind of very interesting. Okay, now let's find the parametric equation. Okay, so I'm going to use x to be x. Okay, y equal to what? Okay, so what did we just talk about? Y is, okay, let's put it up here. Remember, this is the surface of revolution, right? So we have, we have this. So I'm going to put it over here. We're going to use this, right? I'm going to use this. Okay, there was equation 3. Equation 3, using this. Okay, so looking at this, okay, remember when you have surface of revolution, you can parameterize it using the two parameter. One is going to be x. The other one is going to be the theta, right? Using this two parameter. Okay. Okay, and now according to this is the surface. Remember this one here? It's the surface of revolution. So we have x equal to x, y equal to what? Sine x cosine theta, right? So it's supposed to be f of x over here is sine x, right? In this case, it is sine x. And you just put that in. So it will be sine x cosine theta. Okay. What about z? Z equal to what? F of x, which is what? Sine x and sine theta. You got it. Okay, good. All right. And the parameter domain, we want to see the x and the theta, the two parameter. What are the restriction on them? Okay. X is between what and what? 0 to 2 pi? Yes. It says here, x between 0 and 2 pi. And then what about theta? Theta between what and what? 0 and 2 pi? Yeah, so 2 pi. Okay, because one rotation, right? Okay. So yeah, that's how you do for surface of revolution. Okay. You can use x and theta to parameterize it like this. Okay. All right. And then if it's a surface revolution about the y and z axis, you're going to change this. Okay. So if it's about the other axis, you're going to switch it. Maybe y equal to y and then express the other two. Okay. So the idea will be similar. Okay. Next one, we talk about tangent plane. Okay. So what's the tangent plane? Here's a picture of a tangent plane right here. Okay, here's a surface, here's a point. A tangent plane here is kind of like this one here is patch over there. Just touch it over there at that neighborhood. Only touch that one at one point. Okay. Now And then this surface over here is traced out by this vector function. It has x, y, and z component. Okay, and then you see this. If you keep the u constant, you get the C1 over here. If you keep the v constant, you get the C2, this orange group curve over here. Okay. All right. Now, what happened? If you keep the u here constant, okay, you put u equal to u naught, okay, then you get the C1 over here. This one over here corresponds to, okay, let me draw this. This one here corresponds to this one over here, okay? They're corresponding right here. Then this curve is going to map to this curve, okay? The tangent vector to the C1 at this point, how do we do that? We take the partial derivative of this R with respect to V. Because you keep, at that time, we keep this U here as a constant. So the only changing parameter is the V. So along this group curve, only V is changing, U is fixed. So you're going to take the partial derivative that with respect to V, okay, on each component, and that is the partial derivative R with respect to V, okay? And in the picture, you can see that I draw it over here. I see a circle, put a circle here. This is the one right here. This one here is the partial derivative R with respect to V. Basically, it's kind of like the tangent vector of this curve at this point, right there. Okay. And similarly, if we have this one, this group, this horizontal segment, it's going to map to this group curve over here. And then partial derivative of that with respect to U, okay, remember the V is fixed along this one. So partial derivative of that with respect to U is this tangent, the tangent over here, right there, okay? And I put a triangle over here to see, that you see the correspondence right there, okay? So, and then what happened here if this and this one, if the cross product is not zero, then the surface is called smooth, okay? It has no corner. So for a smooth surface, the tangent plane, remember when you have a plane and you have this A and B, two non-parallel vectors, right? Then for that surface, it's going to be determined by these two vectors. Okay. Now at this time, we have two vectors on this tangent plane. One is this on that plane right there. One is this R of V. The other one is this vector R of U. Okay. They're going to determine that tangent plane right there. And just like this tube vector. Then how do you write it? Remember in the past when we say to write the equation for the plane, it's important to find the normal vector, right? So if you can find the normal vector, you can write the equation on the plane. And if you have a point on the plane and a normal vector, you can write the equation for the plane. But how do you find this normal vector over here? Normal vector has to be perpendicular to every vector in the plane, right? So in order to perpendicular to that, then remember the cross product. The cross product of these two is going to be orthogonal to this one and this one. So you take the cross product of this vector and this vector. This vector over here is the normal vector. Okay, let's look at this example. Example 9. Find the tangent plane to the surface with this parametric equations. at this point 1, 1, 3. So at this time, we actually know the point, right? So we know this point over here is 1, 1, 3. And then we just need to find the normal vector, okay, in order to write the equation for the plane, okay? So first of all, let's write down the vector equation for that surface right there, okay? So what is the vector equation for the surface? If you know the parametric equations, all you have to do is what? Just plug it in, each component, right? So you're going to put this into the x and put that into y and put that into the z, okay? So that will be u squared, v squared, u plus 2v, okay, each component. Now we're going to compute. Remember, we're trying to compute this one and this one, okay? In order to find the normal vector, we need to compute this one, and later take the cross product, right? So let's compute this one and this one. So what is the partial derivative of this with respect to u? What's the partial derivative of this with respect to u? To u, okay? And then plus, hold on. Partial derivative of this with respect to u. Yeah, maybe I forgot some. Okay, maybe I erased them. Yeah, it is to, yeah, you got it, to u. Okay, so that is 2u, okay, in the I component, and then plus k. Okay, that's that one. What about partial derivative of this with respect to v? Huh? 2vj plus 2k. You got it. Good job. Okay. All right. So once you find this one and this one, we try to find the normal vector, right? So we're going to take the cross product of these two to find the normal vector. So we're going to cross this. So remember, okay, let me draw this picture so you can see RU, and then you have RV, and then you take the cross product, and then you will get this. This is a normal vector, right? So you take the cross product of these two, this one and this one. Okay. Okay. Now the guy remember how to take cross product. Okay. So we construct this. That will be the symbolic determinant of this 3x3 matrix, right? What's the first row? IJK. Yeah. The second row. The second row will be this vector, right? RU, right? So we put this one 2u 0. So that will be 2u, and then there's no j component. So that will be 0 over here. Okay. And then after that is 1. Okay. What about RV? So that will be 0, 2v, and then 2, right? Okay. All right. So because this one here doesn't have the I is equal to 0. So 0, 2v, and then 2. Okay, good. All right, and then we calculate this cross product, and that will give you the normal vector over here, right? Gives you the normal vector. And now we need to figure out the u corresponding. Okay, we have this point here, 1, 1, 3. Okay, so we have this point. This point here is 1, 1, 3. Okay, and we also have the normal vector, but we need to figure out for this point right here, what's the corresponding u and v? So we know that x equal to 1, right? We know that this equal to 1, and this y equal to 1, and z equal to 3. So what does u and what do u and v equal to? 1 and 1, yes. From here, you see that actually is the U will be 1, V will be 1, and then you're going to have X equal to 1, V equal to 1, and Z equal to 3, right? So that way, this is 1, this is 1, and this one here will be 3, right? Okay, good. So U equal to 1 and V equal to 1. Okay, you got it. So now, once you find out the corresponding U and V, you can actually substitute here. So at this point, you can find the normal vector. So at that time, you can just put, so here you have U equal to 1, V equal to 1, and you're going to put it over here to find this normal vector at this point, okay? So that will be negative 2i, negative 4, and here is 4. Okay, substituting this in here. So you get this normal vector will be this. So the normal vector is actually the green one right there. So it should be negative 2, negative 4, and 4. So we found this normal vector over here to be negative 2, negative 4, and 4. Okay, so and then at this point, 1, 1, 3, that's the normal vector. Okay. Do you guys remember how to write the equation of the plane when you're given a point and a normal vector? If you forget, here I put it up here, so to refresh your memory. A scalar equation of the plane go through this point with this normal vector is given by this equation. Okay, just use A times X minus X naught plus B times Y minus Y naught plus C times Z minus Z naught equals 0. Okay, so go back over here using that equation. Using that, right? So what's the equation for the tangent plane? We know that passing this point 1, 1, 3 with the normal vector over here. This is a normal vector. What's the equation for that tangent plane? What should I put over here? That will be negative 2, right? Negative 2 x minus 1. Minus 1. Okay, and here will be what? Minus 4, right? Y minus 1. Okay, and the next one will be plus 4. And then Z minus 3. Yeah. And then equal to 0. Okay. So that's the equation for this tangent plane. Okay. Okay, now the last topic here is surface area. We do have a lot of topic today. Use the surface area, then you can try to, we actually use a Riemann sum, okay, right here. For each one, this delta U, delta V, this subrectangle go over here, is going to map to this. Think about it as a patch on this, in the surface over here, okay? And then we can approximate this surface here is actually is the absolute value of this magnitude of the cross product times delta U, delta V. Okay, how is it this? How did this come from? For the parallelogram, this parallelogram here, the area for this parallelogram, remember, is the cross product, the magnitude of the cross product of these two, right? So when you take the cross product of these two, and then you will get this. And you're using the parallelogram here to approximate the area of this patch right here, okay? Now, after all this, you take the limit of the Riemann sum and you get the surface area. The surface area is actually equal to the double integral of this, the magnitude of the cross product of RU and RV, and then over the region D. Okay, over the region this UV is in. That was the surface area over here. Okay. The RU here is the partial derivative with respect to U. RV is partial derivative with respect to V. Okay, let's try some examples so we can see how we use it. We try to find the surface area of the sphere with radius A. What's the area of the surface area for this? Anybody remember the formula? That is 4 pi. Okay, if you don't, that's okay. Let's discover the formula, okay? Okay, let's try to use this one, the surface area, this one right here, to calculate use this formula to calculate the surface area, okay? First, we're going to parameterize this surface. We did that last time in example 4. We parameterized it using the spherical coordinate system that we got this, right? And then the parameter domain will be this one, okay? Then we're going to, in order to find this surface area here, we need to find this cross product and then take the magnitude of it. So let's find the cross product. Okay. The cross product of this R phi and R data. Remember, the two parameter in this case is phi and data, the two parameter, okay? So this one, you're going to first take the partial derivative with respect to phi, and then here, partial derivative with respect to data. And then you find the cross product of them. So what should I put over here? This one, partial derivative of this one here, partial derivative of the first component, which is x, with respect to phi. Okay, so let me write it down. So that is partial derivative of this, the first component with respect to phi. And then this one, partial derivative of this with respect to phi, partial derivative z with respect to phi. Okay, so this will be the partial derivative r with respect to phi. Okay, the next one are partial derivative with respect to data. Then you just take each component and then take partial derivative with respect to data. All right, and I actually did the calculation, right? Like this, and then after that, you're going to find the magnitude of this, and it turned out to be this number, this quantity, okay? And then because now we're going to use the formula that we're given, this one. So the magnitude of this cross product is going to be this. And then dA, what's dA? Remember the A here, the dA over here is, the phi over here is going to be 0 to pi, okay? And the data over here is 0 to 2 pi. So the region D is this. It's a rectangle with phi between 0 and pi, data between 0 and 2 pi. Then you're going to enter over here. So we place the dA here by d phi d data. Phi go from 0 to pi, and then data go from 0 to 2 pi. And then do the calculation, and the result here turned out to be, what's the final result? 4 pi a squared, okay? So if some of you already remember, the surface area for a sphere with radius a, it should be 4 pi radius squared, right? 4 pi a squared. So they agree with it. The surface area of the graph of a function. For the special case of a surface with equation z equal to a function of x and y, xy lies in the D, okay, and f has continued partial derivative, we can take x and y as parameter. Remember last time we talked about if z is a function x and y, we can actually take x and y as parameter, okay? So the parametric equation are x equal to what? X equal to x, y equal to y, And then Z equal to what? F of xy, right? Okay. X and Y. Okay. Then now you're going to find the possibility of R with respect to X, and then also find the possibility of R with respect to Y, and then you compute the cost product over here, and then find the magnitude of the cost product, okay, this. Then you come up with this surface area formula. The surface area formula, okay, but let's go back to the arc length formula and then try to compare this. Do you guys remember what's the arc length formula for the when you have a arc like this, right, from A to B? Okay, what is the arc length? It's the integral of, okay, so this one here is the dx, right? So it's the integral of the differential arc length. And if you put the dx outside, then inside the square root, you have 1 plus dy dx square, right? Okay, and then x over here go from 0 to, the x here go from A to B, right? Okay, let me draw the picture. So this arc length over here is equal to that, right? Now, this one over here for arc length. Now, what about surface area? The surface area here is going to be, remember from the formula we have, it should be equal to the integral of this. Okay, so that will be that, and then dA, and then over the region D. Okay, now let's compare this with this one. This one over here is the square of 1 plus dy dx squared. This one over here is partial derivative with respect to here with respect to x, and here with respect to y and z. And you see this one here, y is a function of x. And you pick the derivative of that, and you see with respect to x squared. And here d is a function of x and y. So it's the partial derivative with respect to x, and the square partial derivative with respect to y and squared. So you see the relationship. This is for the surface area, and this is for the arc length. Okay, I think the rest here you can just read the book, okay? All right, so I think I'll let you guys go. Okay, thank you for coming.